Hello students, welcome to EPG Pathshala. I am Dr. Savita from University of Delhi. Today we are going to discuss about the module Mechanical Properties Part 3, which is from the paper Electronic, Magnetic and Optical Properties of Materials. So students, let us see what we are going to learn in this module. We are going to study about the various strengths, which are number 1, tensile strength, number 2, compressive strength, number 3, shear strength, then the bending strength, torsional strength. Then we are next going to study about the elastic deformation, and in the end we will study the stress-strain behavior. Strength. It may be defined as the capacity of material by virtue of which it can withstand or support an external force or load with rupture. It is expressed as force per unit area of cross section. A material has to withstand different types of load, for example, tensile, compressive and shear load. Accordingly, one may broadly classify strength in the following two categories. Number 1, we can divide depending upon the value of stress. The strengths of a metal may be elastic or plastic. Then secondly, depending on the nature of stress, the strengths of a metal may be tensile, compressive, shear, bending and torsional. Now we study all these types of strengths. First is the ultimate strength. It is a strength in which it is the load required to fracture a unit cross section of a material. Then next is the elastic strength. Elastic strength is the value of strength corresponding to transition from elastic to plastic range, that is, when material changes its behavior from elastic range to plastic range. This is known as ideal stress value and is used to define elastic strength of a material. The next is the plastic strength. It is the value of strength of the material which corresponds to plastic range and rupture. It is also termed as ultimate strength. The ratio of ultimate strength to the working stress of a metal is termed as factor of safety or factor of ignorance. This greatly depends upon the nature of loads or stresses. Usually, the following values of factor of safety are generally kept with various loads. So, there are 3 or 4 kind of loads. The first one is the dead load, which has the value 4 or 5. Then there is a live load, which has the value of 6. Alternating kind of load has the range of values from 8 to 12. Shock loading has the values ranging from 12 to 15. One adopts the lower value of factor by safety by ensuring the metal to be without any defect, which is done through non-destructive tests. In determining the reliability of the design, the factor of safety is of great importance. The topic is tensile strength. It is the maximum tensile stress which a material is capable of developing when subjected to loading up to rupture. Mathematically, tensile stress equals to maximum tensile load divided by original cross-sectional area. The tensile stress is expressed in newtons per mm square or meganewtons per meter square. In actual practice, a given specimen is always subjected to a tensile stress less than the working tensile stress. Tensile strength is obtained from the following relation. Tensile strength equals to maximum force in kilograms divided by original area in square centimeter. Tensile strengths and tensile modulus of few selected materials are given in the following table. This table shows the tensile strength and tensile modulus of few selected materials. Tensile strength is in newtons per mm square and tensile modulus is into 10 raised to the power 3 newtons per mm square. As we can see from the table, the maximum tensile strength is for the nickel alloys, where the range of the tensile strength varies from 400 to 1600, while the lowest tensile strength is of the polyethylene high density, where the range of the tensile strength varies from 20 to 40. The highest tensile modulus is shared by the three materials mild steel, ferrite SS, nickel alloys and martensitic SS. The lowest value of tensile modulus is for the material polyethylene high density. Tensile strength is the ultimate strength in tension and corresponds to the maximum load in a tension test. It is measured by the highest point on the conventional stress-strain curve after yielding the stress necessary to continue plastic deformation in metals increases to a maximum. The maximum is point M, as you can see in the given figure, and then decreases to the eventual fracture, which is the point F. The tensile strength Ts, which is in megapascal or psi, is the stress at the maximum on the engineering stress-strain curve. The given figure shows the typical engineering stress-strain behavior to fracture point F. The tensile strength Ts is indicated at point M. The topic is compressive strength. For a metal, the compressive strength is the value of load applied to break it off by crushing. Mathematically, compressive stress is equals to maximum compressive load divided by original cross-sectional area. Compressive strength is also expressed in Newton per mm square or meganewton per meter square. In actual practice, a given specimen is also subjected to a compressive stress less than the working compressive stress. The next topic is shear strength. The shear strength of a metal is the value of load applied tangentially to shear it off across the resisting section. Mathematically, we can express shear stress equals to maximum tangential load divided by original cross-sectional area. It is also expressed in Newton per mm square or meganewton per meter square. Bending strength. For a metal, bending strength is the value of load which can break the metal off by bending it across the resisting section. Mathematically, bending stress is equals to maximum bending load divided by original cross-sectional area. This is also expressed in Newton per mm square or meganewtons per meter square. In practice, the given specimen is also subjected to bending stress less than the working bending stress. The next that we are going to study is torsional strength. For a metal, the torsional strength is that value of load applied to break the metal by twisting across the resisting section. Mathematically, torsional stress equals to maximum twisting load divided by original cross-sectional area. This is also expressed in Newton per mm square or meganewton per meter square. Hardness. Another mechanical property that may be important to consider is hardness. Hardness is a measure of a material's resistance to localized plastic deformation. For example, a small dent or a scratch. Quantitative hardness techniques have been developed over the years in which a small indenter is forced into the surface of a material to be tested under controlled conditions of load and the rate of application. The depth or size of the resulting indentation is measured, which in turn is related to the hardness number. The softer the material, the larger and deeper the indentation, and the lower the hardness index number. Measured hardnesses are only relative rather than absolute, and care should be exercised when comparing values determined by different techniques. Hardness tests are performed more frequently than any other mechanical test for several reasons. Number one, the first reason is they are simple and inexpensive. That is, ordinarily, no special specimen need to be prepared, and the testing apparatus is relatively inexpensive. Secondly, the test is non-destructive. That is, the specimen is neither fractured nor excessively deformed. A small indentation is the only deformation. Other mechanical properties often may be estimated from hardness data such as tensile strength. Next is the Rockwell hardness test. The Rockwell test constitutes the most important method which is used to measure hardness because they are so simple to perform and they require no special skills. Intenders include spherical and hardened steel balls having diameters of 1.588 or 3.175 or 6.350 and 12.70 mm, and a conical diamond, which is a Brinnell intender, which is used for the hardest materials. With this system, a hardness number is determined by the difference in depth of penetration resulting from the application of an initial minor load followed by a larger major load. Utilization of a minor load enhances test accuracy. On the basis of the magnitude of both major and minor loads, there are two types of tests, Rockwell and superficial Rockwell. For Rockwell, the minor load is 10 kgs, whereas major loads are 60, 100 and 150 kilograms. Each scale is represented by a letter of the alphabet. Several are listed with the corresponding intender and load in tables 2 and 2a, which are given below. For superficial tests, 3 kg is the minor load, 15, 30 and 45 kilograms are the possible major load values. These scales are identified by a 15, 30 or 45 according to the load, followed by N, T, W, X or Y depending on intender. Superficial tests are frequently performed on thin specimens. The second table 2b represents several superficial scales. When specifying Rockwell and superficial hardness, both hardness number and scale symbol must be indicated. The scale is designated by the symbol HR followed by the approximate scale identification. For each scale, hardness may range up to 130. However, as hardness values rise above 100 or drop below 20 on any scale, they become inaccurate. And because the scales have some overlap, in such a situation, it is best to utilize the next harder or softer scale. Table A and Table B. Table A represents the Rockwell hardness scales, while the Table B represents the superficial Rockwell hardness scales. Table A, which is the Rockwell hardness scales, we can see the scale symbols from A, B, C, D, E, F, G, H and K, and the major load varying from 60 kilograms to 150 kilograms. Similarly, the Table B shows the superficial Rockwell hardness scales with the scale symbols starting from 15N to 45W, with the major load varying from 15 kilograms to 45 kilograms with the different intenders. Here shows the table giving the hardness testing techniques. There can be various tests as we studied: Brinnell, Vickers micro hardness, Knoop micro hardness, Rockwell and superficial Rockwell. Then according to the different tests, there are different intenders. Then the shape of indentation is also different. The various shapes of indentations are shown in this table according to its side view or the top views. Then the formula for hardness number is also different for the different tests. So we have the complete compact compilation of the different hardness testing techniques along with the shape of indentation, intender, load and the formula for hardness number. Brinnell hardness tests. In Brinnell tests, as in Rockwell measurements, a hard spherical intender is forced into the surface of a metal to be tested. The diameter of the hardened steel or tungsten carbide intender is 10 mm or 0.394 inches. Standard loads range between 500 and 3000 kg in 500 kilo increments. During a test, the load is maintained constant for a specified time, that is between 30 and 10 seconds. Harder materials require greater applied loads. The Brinnell hardness number, which is denoted by HB, is a function of both the magnitude of ith, a spatial low power microscope utilizing a scale that is etched on the eyepiece. The measured diameter is then converted into the appropriate HB number using a chart. Only one scale is employed with this technique. Semi-automatic techniques for measuring Brinnell hardness are available. These employ optical scanning systems consisting of a digital camera mounted on a flexible load and the diameter of the resulting indentation. This diameter is measured W probe, which allows positioning of the camera over the indentation. Data from the camera are transferred to a computer that analyzes the indentation finish requirements are normally more stringent than for manual measurement, determines its size and then calculates the Brinell hardness number. For this technique, surface finish requirements are normally more stringent than for manual measurements. Maximum specimen thickness as well as indentation position relative to specimen edges and minimum indentation spacing requirements are the same as for Rockwell tests. In addition, a well-defined indentation is required. This necessitates a smooth, flat surface in which the indentation is made. Knoop and Vickers micro-indentation hardness tests. Two other hardness testing techniques are Knoop, pronounced, and Vickers, sometimes also called diamond pyramid. For each test, a very small diamond intender having pyramidal geometry is forced into the surface of the specimen. Applied loads are much smaller than for Rockwell and Brinnell, ranging between 1 and 1000 grams. The resulting impression is observed under a microscope and measured. This measurement is then converted into a hardness number. Next is the correlation between hardness and tensile strength. Both tensile strength and hardness are indicators of a metal's resistance to plastic deformation. Consequently, they are roughly proportional. For tensile strength, as a function of the HB, for cast iron, steel, and brass, the same proportionality relationship does not hold for all metals. As a rule of thumb, for most steels, the HB and the tensile strength are related according to Ts, which is the tensile strength in megapascal, is equals to 3.45 multiplied by HB, or Ts, which is the tensile strength in PSI units, is equals to 500 multiplied by HB. So students, let us summarize what we have learnt in this module. This module gives a brief introduction of the strength, tensile strength, compressive strength, shear strength, bending strength, torsional strength, hardness, and its tests like Rockwell hardness test, Brinnell hardness test, Knoop and Vickers micro-indentation hardness test, and correlation between hardness and tensile strength. Thank you.